Okay, folks. Welcome to lecture 9, I think, or whatever. Any questions before we go on in terms of homework or things like that? Again, I'm willing to stay after class if you have homework questions and that sort of thing. I also will have office hours again tomorrow afternoon from, 4 to 5:15, I think is what I put down. So that'll be pretty regular. Just keep an eye on the emails, though. We do have a quiz. We'll do that at the end of the day. Question? Let's see. The first exam I think we've got scheduled according to the syllabus is a week from Thursday. I'm going to put it off until the following Tuesday. So that way you'll have the weekend to study and that sort of thing. Plus, I think I want to make sure you digest the lectures before that, because it'll be chapter 1 through 4. So we're getting into the final chapter here that we'll include in that first exam. Okay, so today what we're going to do is start jumping into probably the most interesting thing about statics is solving problems on rigid bodies. Points were nice, but there's only a few applications of those that we can actually do. What we're going to be more interested in is looking at full bodies, bridges, and stuff like that. And when you get into, say, structural analysis, whether you're mechanical or civil, you will be using statics as a kind of a grounding and to see whether your numbers are ballpark figures. You might be using complicated approaches like finite elements and that sort of thing. But again, you always want to ground that with something that you know. So you can do some simple calculations with the statics to give you an idea of what sort of magnitude, what's the ballpark of the forces of this particular project and that sort of thing. So what we'll be doing is learning how to construct free body diagrams, identifying the forces on a free body diagram, most important step. If we don't identify all the forces, we'll get a wrong answer for sure. Once we have a proper free body diagram, then we'll go ahead and construct equilibrium equations, and then we'll start solving for those unknown forces, and that's what statics is all about. Wish we just had one of these on the side here. It'd be a lot easier instead of rolling it back and forth here. So equilibrium of rigid bodies now. So rigid bodies, again, we talked about are just a combination of particles. And a couple of things that we're going to take advantage of and recall that we talked about in terms of the first couple of lectures. Okay, so we're going to appeal again to Newton's first law there, a body that's static or stationary, or a body that's moving, again, at a constant velocity. And again, think about that when you're on the train, light rail, or something like that. When we're moving, we start moving or start slowing down, we can feel ourselves moving all over the place. When it's sitting still, we're just pushing on the floor there. When we're moving at a constant velocity, we're just pushing on the floor there. So that's an example, basically, of how we can use that. So we've been talking about creating this force couple, and we've been reducing things right and left. And the key thing is where we're going with that is equilibrium. We're going to set that equal to 0. It's got to be equal to 0 for Newton's first law to hold. So we're going to have our we're going to be able to calculate, just like we've done up to this point in time, and take to one point all of the forces, create a resultant. And then take those forces, and since we're moving them out of their lines of action, again, we're going to create a couple. And we're going to be able to move it to some sort of a point there and be able to calculate that. And what 2D equilibrium tells us is that our R, which is composed of an x component and a y component, and we like the Cartesian system for that reason, or we can express it as and we saw that when we were putting together that resultant, basically anywhere on the body, it's just simply a sum of those forces, sum of the x components and the y components. And then 2D, our moment is going to be in the z direction, again, in or out of the board. And again, just looking at how that's created is just simply that expansion of those position vectors, which basically are describing a distance from a point of interest that we've chosen, our point O, to the location of those forces. And when is a vector equal to 0? When? When is a vector equal to 0? Well, based upon our two vectors here, what would make this vector equal to 0? Each of those components will be equal to 0. So the sum of the forces x equals 0 and the sum of the forces y equals 0. We can't drive it to 0 unless each of those component forms are equal to 0. And then the moment's pretty easy because there's only one component there. Ugly looking z there. But basically, those are three scalar equations. And since we're setting that right-hand side equal to 0, that means I can solve for something on the inside. Some x component, some y component, or some z component. And I can solve for those, basically, and then find an unknown force acting from a support or some cable attached to it or other body. Okay, so we'll talk again a little bit. It's a little bit of expansion of what we did before there in terms of points, but okay, so it's going to be this exterior diagram. Remember when we were drawing all the baked potatoes, I was always putting springs on the outside there. And we were talking about I can move the force with transmissibility along its line of action there. And that exterior set of springs basically didn't see any difference from one versus the other. So we're doing the same thing again with this rigid body. It's going to be what happens on the exterior that's important. And it's an isolated mechanical system, but we're isolating it. We're choosing what we're going to isolate. So what we're going to see when we get into structures and start individually looking at individual members, that we can start looking at various pieces, taking them out, and basically creating a free body diagram, setting up our equilibrium equations, and solving for something. So draw it over here where you can see it. We'll just kind of walk through an example here. And I'll let you know that it's a bridge, so if my drawing doesn't look anything like it, at least you'll have some idea of what it was supposed to be. So you've probably seen typical truss bridges across streams and that sort of thing. We'll get to talk about trusses and start solving them earlier or later in the course. Draw a Subaru or something like that. So we have a car there too that's weighing something. So again, this is a mechanical system. It's holding up a car. It's keeping it from falling into the water. What we're going to do in terms of what a free body diagram is, what I'm interested in is the exterior again. So my free body diagram will look like that. So there's a car in there. There's truss members all over the place, but I don't care about those. I'm just going to draw this exterior, because what I'm interested in basically is, if I'm an engineer, I need to design these supports on the end there. I've got to figure out, okay, well, how heavy is it? How heavy is the bridge? How heavy are the cars? Are there earthquake loadings and that sort of thing I need to worry about? What I'm going to do then is replace what the ground is providing that isolated body with the force that it's providing. So I'm trying to push through the ground's saying, or abutment and that sort of thing, and it's saying, no, basically, I'm going to keep you in that position there. And what's causing that might be the weight of the bridge, and it might be located. We might sum up all the forces and find a location for that. We get to do that later in the course. We also have the weight of the car. Now again, notice I didn't draw the car. That's not part of the exterior of this particular situation here. But it is providing something here that my ground has to support. There's forces there that I have to support. Maybe we'll just... so you know where they came from. So this is the bridge weight here in the center. And then we have the car. So all those things are being held up by something there on the ground, those supports. So what?
So the bridge weight and the car weight are considered separate, or?
No, they're part of the forces within this system.
But that's like, would that be considered one force? Is that two different forces, or just one force?
Well, it's two different forces, but yes, you'll be able to eventually combine them into one force.
Okay.
Yeah. So you're way ahead. That's chapter 5. We'll get there before you want to, I'm sure. But yes, you're right. We can do that because we have that ability to add forces. Just like we did a result, we can create a resultant out of that. So yes. But sometimes when we find we're doing equilibrium problems, and we'll talk about that when we get into some of the tougher problems, sometimes it's easier just to keep them as separate forces. Because again, I can sum them up, and I'm going to be doing that when I do equilibrium equations. Okay, so a couple of notes here. We're going to remove the supports. And I'm going to substitute the forces that those supports are providing me. And we'll just put this on the board right now. When we're doing an equilibrium problem, if you don't draw a separate free body diagram, you will lose points, okay? And the reason why is that we're going to be constructing equilibrium equations out of these. And I can't tell, and you probably can't tell necessarily when you're working on it, where those forces are acting. So if you don't have a free body diagram, some of you may be visual solvers and that sort of thing. I agree with that, but again, give me a chance to give you partial credit, because if you do make a mistake along the way there, if most everything's there, I can give you partial credit. If I don't have a free body diagram, you're just going to have to lose points. I can't figure out where you created your equilibrium equation. Was it in your head? Was it the neighbor's paper next door? And that sort of thing. So give me a chance, basically, to give you those partial credit. Okay, so let's talk about the supports. And where we come up with those is from Newton's third law. Nope, I'm missing a G. Okay, so for, again, Newton's third law was for every action or reaction, or every force, you can think of it that way too. There's a force that's equal in magnitude, opposite in direction, and the one thing we don't necessarily think about but is important, it's collinear. And again, that means acting along that line of action there. Okay, so just think of a column on the ground, and it's not falling through the ground or anything like that. It's just standing there. We might go look at it. It might be a telephone pole or something like that. What we're saying is we can draw this exploded view here. Where's my red? So the column itself has some weight, and the weight is acting towards the center of the earth there, or down in our particular case there. What we're saying then is that my support there on the earth, whatever it is, it may be deep in the ground, that sort of thing, but it's basically going to be the same in magnitude, opposite direction, and then they're acting along that LOA. So if I take it apart and look at it that way, basically like that, if I look at the earth, it's going to be doing something like this. If I look at the column, it's going to be providing some sort of a load down. So basically that's saying that Sean's here with your homework. Which ones do we have?
This is homework 2.
Homework 2, okay.
Homework 3 I should have done by Thursday.
Okay, so we're getting homework back. We'll pick this up at the end of class. I know you all want to look at it right now. Thank you, Sean.
Bye.
Yes, everybody clap for Sean. Okay, so basically what we're saying then is that we got to keep thinking about Newton's third law there. It's going to be equal and opposite. And what we're going to do now is we're going to look at, one other note I think I was supposed to put down. Yes. Because we'll talk about this when we look at these examples. The rule of thumb, if we think about our free body diagram, if there's some motion that's impeded by pulling it away from a support, when we take it and say, okay, I've got a support here, if that support is saying, I'm not going to allow you to go into the ground, okay, what we're going to do is then when we replace that support, when we pull that isolated mechanical system away from that support, what we're going to do is substitute a force. Now, we'll talk about that when we start looking at some of these examples. What we're going to do is we're going to go through and look at supports that we're going to remove and what directions and what sort of unknowns are involved with that. So you've got them in your book, but I've broken them up a little bit differently in terms of unknowns specifically. But I want you to think about them because you don't necessarily have to take a picture of all of these and put it on your cheat sheet and that sort of thing, because when you think about what they're doing, you'll be able to understand which direction the forces are going in. Sir?
I just have a quick question. My picture on the right, is that just an equal sign? That means they're equal and opposite direction?
They're, equal in magnitude, opposite direction, and they're acting along that line of action. So Newton's third law right there. Yeah, if you want, we could do magnitudes are equal. And it's obvious from the picture the directions are different and the line of action. Good point, though. That's a good way of representing it that way. Sir?
That's the normal, right?
Huh?
That's the normal?
Is that normal?
Normal force.
Well, yeah, we'll get into that when we start talking about it. Yeah, it is normal to the surface, and that'll be an important thing to know. Yes, you're right about that. I was going to jump into, you're jumping into the next page there, but yes, it will be normal to that surface, and I'll show you why when we talk about thinking about motions impeded. And I need to, so you've got your handout, but you don't have everything written down, do you? So I'm going to force you to fill out your little sheets, but we'll kind of talk about what we're seeing when we fill out our sheets there. Now, probably the easiest, now this isn't necessarily a support, although it could be, a cable could be a support, but again, it's another attached body. So there's a cable attached to that. Now, the nice thing about a cable is we can go out and measure it, and we can figure out what its angle is with respect to our isolated body. So our isolated body doesn't look a whole lot different. It's that bar there. But what I'm going to do now, when I cut it away from that cable, so the cable now suddenly disappears, I'm going to substitute in a force. And think about it. The cable's probably pulling on it like that. Maybe not. I don't know. But it may be pulling on it. So we're going to substitute what we think is going to be the force. But the nice thing about that is that we know its direction. If I can measure the cable and its angle of incidence there on the body, then basically my force has to go that way. A cable can't apply sideways forces and that sort of thing. So the nice thing about that then is I'm down to one unknown. Basically the unknown magnitude. The angle, its direction is known. Now again, when I say the angle, think about it, we like to break it up in terms of x and y components, right? But the angle, if the angle is known, that means that fx and fy are a known quantity. If I do fx over fy, basically it's going to be the same number, basically. So it will be basically the only unknown in that is going to be the magnitude. Now the next thing is some sort of a smooth surface. And now I don't even have a flat surface there. But going back to your comment on normal, again, think about what motions are being impeded here by that surface. Well, the surface is going to say you can't come through me. I'm a hard surface. I might be made out of marble or something like that, or concrete. What it's going to say is that we're going to substitute that. We're going to remove that surface, but basically we're going to substitute a force that's going to be perpendicular to the tangent of that of the surface at that point. Now, if the surface is straight, that's a pretty easy one to figure out. But again, the key thing is that it's perpendicular to the surface, not to the body, okay? Because it's the surface that's saying, no, you're not going to pass through me. Now, if I want to push this way, somewhere along the tangent there, look, there's no force there. That perpendicular force there is not going to restrain me from pushing it along that tangent. So the only restriction, or the only motion impeded there, is basically going to be some sort of movement into the surface there, and we're going to measure it in a perpendicular.
So we're excluding gravity then?
No. We'll include gravity in the body some other point in time. Right now, what we're doing right now is just talking about removing supports, and what sort of forces are we going to substitute for them. But we will get into gravity and looking at our problems and stuff like that. But yes, that force, that support may be providing, the only thing it may be holding up is gravity or something. We don't know. There may be other things on there. There might be a car on it or something too. Okay, another one that we run across is what we call rollers. Now, we see these a lot on bridges and stuff. When you go over bridges, you hear the bam, bam, bam. Those are expansion joints. Basically, bridges have to expand in the heat and contract in the cold. And if we don't create these joints, basically, what we're going to find is roadways buckling and that sort of thing. So these rollers we represent in terms of static with a wheel or a little triangle with wheels and stuff like that. But they're the sort of things we see on bridges. So it's basically saying, I'm going to lay you on here, and if you expand, I'm going to let you slide. And if you contract, I'm going to let you slide this way. So again, think about the motion restrained. I'm not going to restrain any motion along the direction of the roller there, parallel to the surface. The only motion I'm going to restrain is vertical. Now, the one thing I'll add, and just think about this when you get into EIT exams, we like to think of it in terms of rollers. It makes sense that the force can only be that way, but it could be the other way in some exams. So be very careful with that at EITs. But the key thing is its direction is known. It's perpendicular to that surface, once again. So the only unknown is its magnitude. And then the final one we'll look at there, when we get into machinery and complicated things like that, there's things where bodies are connected via sliders or a slot. And again, think about the motion restrained. Along the direction of the slot or the slider there, I can take that and move it along there, and there may be a little friction, but we'll get into that later on in the quarter. But we're not going to say that there's any sort of force there right now until we get into friction and that sort of thing. So, and usually we grease those things well enough that it's allowed to freely move in that sense. So again, the only force that's acting on that is going to be perpendicular to the surface that it's contacted to. So in this particular case, it's a slider, it's a bar. It's not going to allow me to go this way. The slot is not going to allow the bar to go that way. One unknown, just the magnitude. We know its direction. In this particular case, if we draw our y in the vertical direction, I don't even have to worry about x because I know it's all going to be y. Okay, so that's the grouping of ones that exist with one unknown. So again, it's a little bit different than your book, but again, I want you to think about it in terms of that motion impeded. The next ones we'll look at are now going to be two unknowns. And this is going to be, say for example, now it's on a rough surface. So there actually is some sort of friction maybe, or maybe it's set in a notch. We do that a lot of times too. Well, again, think about the motion restrained. There is going to be restraint from the surface itself saying, I'm not going to let you into me. But there's also going to be some restraint there in terms of it's not going to allow you to slide along that tangent either. So what we're going to do is substitute in the directions of that force. Now, the key thing to note here, too, is that there's really only one force. Okay, so we're substituting in one force. The force has an unknown, it's a vector, though, so it has an unknown magnitude and has an unknown direction. So we can show it this way, but most of the time what we're going to want to do is break it into x and y components, because we're going to want to plug those into those scalar equations there. So this isn't two forces, it's two unknowns of the same force. And basically what we're saying is we don't know how x is related to y in this particular case, because we don't know how this force is angled there. So we have two unknowns, one unknown force, two unknown components to that force that we have to solve for. And again, when we get our scalar equations, then I need to make sure I have two scalar equations available to solve for that. The other common one we see there is what we call the pin. And we see this a lot in arches and that sort of thing too. Again, the pin is not going to allow it to go through the surface there. It's not going to allow it to pop off. And then it's also not going to allow it to move along the direction of that surface either there. So again, it's one unknown force but unknown direction. We like to break it into x and y components because that's my scalar equations again. But it's two unknowns, one unknown force. And this will be real important when we start looking at special equilibrium equations of two forces and three forces. Okay, and the last one we'll look at basically is the built-in or frozen pin. Occasionally you'll see that in terms of certain problems. Note, when we go back to the pin here, again, we're substituting forces in the x and the y direction there. But again, think about that pin. If there's a pin there, if I try to rotate that body, nothing really stops me from rotating, right? It's free to rotate. And all the ones we've talked about previous, there's no restriction on rotation at all. This is the only one that's going to have a restriction on rotation. And this is where we're going to have our cantilever beams and that sort of thing. So what we're going to do is substitute in what we had with the pin before, those x and y, z components. So it's an unknown force, but also there's a restriction in it in terms of moment. It's not going to allow it to rotate. So if I try to rotate that frozen pin or the built-in condition is going to say, not only am I not going to allow you to go this x direction or the y direction, but I'm not going to allow you to rotate either. Now, the key thing to note there is then there's three unknowns there. How many equations of equilibrium do I have in two dimensions? Three. We have the x, the y components of the resultant, and then the moment. So when we do this particular body, we have to be careful in the sense that when we isolate this or pull it away from the support, I've got three equations of unknown. I have three unknowns, and I only have three equations of equilibrium. So I can't have a whole bunch of unknown forces there in that particular one. So I have to make sure that I've solved for other things along the way there. But again, it's important for you to note, if you want to put them down on your cheat sheet, go ahead, that's fine. But the key thing is think about what is it restricting, what motion is being restricted, and what I'm going to do is substitute in a force. No, it's going to resist against any sort of rotation. Say, for example, if I have a force that's pushing up on that thing. Well, again, if I have a force on the end here, and I'm holding it at this point, it's not only going to want to push me this way, but it's also going to rotate the body. It wants to rotate the body.
Like the built-in one. I was thinking that the moment would be holding it up, so it wouldn't be this way.
Might be, unless there's a force pushing up this way. But yeah, if the force is going the other way, it'll go the other direction.
Oh, okay. So
But yeah, you're right. And the nice thing about that is, remember we talked about that when we were doing particle equilibrium. I can choose the wrong direction, and the sign will correct me.
Yeah.
And we're going to have that same situation here. If I choose the wrong direction for that moment, and I put them in the equilibrium equations properly, if it comes out minus, then it says, oh, I just chose the wrong direction.
The moment should be restricting motion.
It's restricting rotation.
Rotation, yeah.
Yes. Mm-hmm. Yeah. So yes, think about it in terms of that. If there's a force pushing up on that, it'll probably look that direction. If the force is going the other direction, it'll want to rotate. Yeah, it'll provide a moment capacity in the opposite sense. So you're thinking like a structural engineer. Good. We'll make you a civil yet. May not want to be, but. Oh. Okay, so what we're going to do is we're going to solve a real problem. And a couple of problems here. They're very similar, not very exciting. There's no trusses and that sort of thing. But basically, we've got a couple of plates here that have some loading on them. That's 4 inches. Sure, I did that right. Good, okay. So what we've been asked here is we've got a couple of plates here that have some sort of, well, actually a similar loading on them, both of them there. But our support conditions are a little bit different. We have a pin at A, and then we have a roller at B. So what we're going to do is kind of walk through those steps that we did before with the particle equilibrium. We're going to walk through those steps in terms of solving for the free body diagram, setting up a free body diagram that makes some sense to us and that we're going to then be able to create equilibrium equations from. So what we'll do is just simply go through those same steps in terms of constructing the free body diagram. Now, what we're going to want to do is consider what bodies we're going to want to isolate. Now, it doesn't make a whole lot of sense here because it's obviously, what we're going to want to do is just pull that plate away from the supports. But when we get into looking at trusses and other such bodies or combined elements there and stuff, we're going to be doing a lot of free body diagrams. We don't have to do just one free body diagram. We're going to have parts that we can isolate and then calculate forces for them. Our second step going to be pretty easy with this one. It's just that external boundary. But again, like we did with the truss in that earlier example there, I'm not drawing the car and the truss elements and the stuff. I'm drawing what I'm interested in terms of the outside there. So when we draw this, we're basically trying to isolate those unknown forces that we want to find. So in this particular case, I've removed that. I created an isolated boundary here of my plate. So I've removed those supports from it. So my next step Okay, so we're going to put all of the forces. That's the tricky thing. Because again, if we forget one of them, we'll get the wrong answer. So we're going to put the known forces on it. Well, we've got that 50-pound there. And the 40-pound is acting there. So that's my two known forces. We obviously want to get those on there. And usually when you're drawing a situation or isolating a situation, you want to have a known force or two on there, because if everything's unknown, it'll stay unknown, because you need something to be able to calculate against there. Something needs to be known. Okay, then our next step is those unknowns. Let's get those unknowns in there. So there's a force there at the roller, and again, the roller, I'm going to put in the line of action of that force that's going to be perpendicular to that surface that it's sitting on there. Now, I drew the force probably in a direction that you're all uncomfortable with, but again, I'm drawing that so you have some feel for how statics will self-correct. The other one is going to be my pin. How many unknowns in a pin? 2. So I'm going to have an unknown force and an unknown direction. So I've got an unknown direction there. I've got 2 unknowns there. And then I've got a third unknown here because I know its direction.
Isn't known the other way?
It's our little secret. I'm going to show. There's a reason why I did it. There's a method to my madness here. Now, we don't have any of these, but there may be weights and stuff too. In this particular problem, there isn't a weight. And a lot of times in statics, you'll find problems where the forces that are put on it are so big compared to the weight of the object. You'll see that a lot of times in trusses and stuff, that basically will just ignore the weight. But realize it's there. And again, as you refine your analysis, when you get into structural analysis, you start looking at things like that. But yes, that's in the wrong direction, and there's a reason for that, because what I'm going to do is show you how it'll correct itself. As long as I get the direction correct, the line of action correct, then signs will correct me in terms of whether I'm going the right way or not. And it actually works for both. Then the fourth step, is generally you want to label it so you can kind of keep track of things. Mm-hmm.
We're doing A or B?
Oh, we're doing A right now. Okay. Yeah, so that's, yeah, we'll look at the next one in just a second here. But yeah, our first one is A.
I'm just confused.
Good point, good point.
The A force is at an angle and the B force is straight up.
Oh, let's think about that. Okay. Why is that straight up? We talked about that, right? It's perpendicular to the surface that it's rolling on. The roller is not going to prevent me from doing this. The pin, however, says you're not going this way and you're not going this way.
Yeah, I didn't see that there weren't any rollers under the triangle.
Yeah, okay. So yeah, the picture is not very clear. Sorry about that. So we're going to label it.
On the exam in the future, are they going to be labeled as a roller or pin, or are we going to have to just interpret the picture?
I usually give you a description describing it because I'm an engineer, and engineers basically need to have as much knowledge as you can. Be aware, though, on EIT exams and that sort of thing, they'll just give you a roller or they'll give you a pin and stuff like that. So be comfortable with both, but I will always put some sort of what your support condition is. So, and I always encourage you when you do that, especially since we're doing a quiz today, read it. You remember the old adage of measure twice, cut once? In exams, read twice, solve once, okay? So make sure you read through it a couple times. A lot of times I only ask for a part of the problem. I may not ask for the whole problem. So don't get yourself all caught up solving a whole bunch of stuff that I'm not going to grade. And you'll find that too in the EIT exams and stuff like that too. They're sometimes a little confusing, so it helps to just kind of read it a couple of times. And I'm also here to answer questions. When I give exams, I'm here, again, engineers, when you're solving a problem, you try to get as much information as you can. So if you don't understand something, raise your hand. We'll talk about it. I'm not going to give you the answer, but I will help you at least see what's there. Okay, so label also includes things like adding the coordinate axes. It may be on the body or may be off, but again, I'll probably choose something like horizontal as x and then the other thing is necessary dimensions. And there may be lots of dimensions on there, but again, what you need to at least show on there are the necessary ones. You can show them all if you want. That's comfortable, makes you comfortable, fine. But the reason why we do that is, again, remember, summing forces is just simply summing x components and y components. But summing moments, we've got moment arms. And we're going to need to know how far we're moving forces out of their lines of action to some point. So we're going to need those distances. So we got the 4 inches there, 20 inches in the horizontal, and then 10 inches in that direction there. And the key thing is that when we're, the other thing then too is, when I break that up and label it, I can come back and, so this force now has a name. We'll call it F of B. And if you want, you can even call it F of By, because we know it's only acting now in the y direction there. And then what I'm going to do is substitute in the two unknown components, because again, equilibrium equations want things in terms of those scalar equations. So I'm going to remove the angle there and everything and substitute in the two unknown components of that particular force there. And what we end up with then is three unknowns. Now, when you draw free body diagrams, most of the problems you'll have, it will be very obvious what you're drawing. But when you get into the more complicated things, you might find yourself drawing 2 or 3 different free body diagrams and find one has 5 unknowns and one has 2 unknowns and that sort of thing. So you might find yourself, stuck with a couple of things, but you can draw different free body diagrams. You'll find that there's combinations of bodies that may give you what we need in terms of unknown equations. Okay, once we've established this is our free body diagram. This gives me the information I need now to construct my equilibrium equations. That's why this step's so important. If we don't have this, then we basically don't have any way of justifying setting up equilibrium equations. So equilibrium equations, what we'll find is then we've got to set our moments equal to 0, our Rx components equal to 0, and our y components. Now, one of the things we'll find is that when we talk about moment is equal to 0, that means moment anywhere is equal to 0. So it can be on or off of the body. But what we want to do is find a point where we can get some of these dimensions, because again, we need moment arms. So think about points in terms of where I want to measure. Now, I'll take it at A. Now, a couple of nice things about taking it there, too. Another nice thing about thinking about this is think about FAX and FAY in terms of their contribution to a moment equation. 0. There's no moment arm, right? So one of the nice things, our workhorse when we get into rigid bodies is going to be this moment equation. And we're going to find that it's nice. We can take this moment equation. What we want to do is move it to a point where we can get dimensions, and also a point where we can eliminate some unknowns. So if I can move it to this point A here, I've eliminated f of A completely. It's component x, it's component y. It can't contribute because the moment arm's it goes through that point. There's no moment arm for that force. Now, when I set up my equilibrium equation, I'll set moment is equal to A, and then I'll choose my positive convention. And again, I'm choosing it for this equation. And moments are twists. So whether the force is negative or positive doesn't matter. It's how it's twisting the body. So the 40, when we think about A there, we got this 40. It's going to want to twist the body in now a negative sense. So I'll have 40 pounds, 10 inches, and then a negative sign, because it's going to want to rotate me in that other sense. Think about the 50. So that 50 is 4 inches over, but again, it's going to want to push me this way, but it's also going to want to rotate about A, that same direction there. Now again, note that these moment arms are very simple. They're all going to be those perpendicular distances, since I've broken my forces into x and y components there. And again, it'll have a negative sign. And then the only other force that will contribute there is my FB of y, the one that the young gentleman said, boy, that just doesn't look right. Let's think about that. I put FBY now, it's an unknown. And it's 20 inches away. What's its sign?
Negative.
It's going to be negative also. So when we look at that, everything's negative. When I get done solving that, what I'm going to find is a negative 30 pounds. So it says my magnitude's 30. I just chose the wrong direction.
Inch pounds,
That's a good thing. Think about that. See, we're going to my F of B, I'm going to move over to the other side there, but I got the inches there, right? That's why I say carry around those units, because a force should be in pounds, not inch pounds, right? A moment should be. Everything in here is inch pounds, but good thinking. Question?
I have a question. So now, as you see, for like 40, we did like 10 because that's the distance away it is from A. And for F of B, we did 20 because that's how it is far away. But the 4 for the 50, isn't it supposed to be like the end of like the hypotenuse of the triangle, like the 10 and the 4? Like, why is it a 4 and not like the...
Because it's going to be the perpendicular distance to that force. My force is acting vertically down, so my perpendicular distance is going to be a horizontal direction there. If I do my cross product, yeah, I can do that. Anywhere along the line of action, it's fine. But again, I'm looking at this in terms of a scalar approach. And my definition of a moment is always going to be the magnitude times that perpendicular distance. And it's a good way to think that, because even when you do cross products, it's easy to screw up, and you can sit back and think about that. OK, so I just solved for that. Once I've recognized that was the wrong direction, I need to make sure that when I do my other calculations, I have it corrected. So go back, fix it. But the nice thing is statics will give me the right direction there. My next step then is choosing one of the components of R. In this particular case, I'll just do F of y, and I'm going to choose the up direction as the positive convention for this equation. So I sum up my various pieces there. I have FA of y. It's drawn in the positive direction per my picture there. So I'm going to put it in as a positive. The 40 doesn't participate in this because we're talking about the y direction. 40 is going to be in the horizontal direction there. I do have the 50. That'll be positive or negative?
Negative.
Negative.
Plus your FBY.
Plus FBY, which is 30. And that's it. OK? So now, with my moment equation, I was able to solve for this piece. Now I start summing the x and y components there. And again, since it is a vector, make sure you give me not only the magnitude, but the direction. And then our next equation will be the x components there. So I'll just look at the various pieces there. I got the FAX. I got the 40. The 50 will not participate. The BY will not participate because they're acting vertical. So that's an even easier equation. And since I've got it going in the same direction there, where is it? And it's acting in the opposite sense there. And then at this point in time, again, if we're designing our pin and that sort of thing, we might be interested in the magnitude, because we're going to design the pin for the force. The pin doesn't care which way the force is going. It's going to be interested in how big is it. So again, we just use our Pythagorean's theorem. And then if you're interested, basically just go ahead and follow through there with the calculation of Pythagorean's theorem, your inverse tan, plug that in basically, and away you go. So you may be asked for that, you may not. Depends on the problem, that sort of thing. But again, as a designer, we're going to be interested in finding out what that force is. I want to make sure you guys have enough time. What I will do is post the solution on the web page under the handouts section there so you can see the other problem. The only trick with that is that our force here will now be at an angle because it's going to be perpendicular to that surface, not perpendicular to the body itself.